Hey chemistry students, this is Mrs. Miller, and today we're going to be talking about the properties of acids and bases as we are in our acid and base unit. So yesterday you guys would have done the kitchen chemistry to get your feet a little bit wet in what it means to be acidic, basic, or neutral, and today we're going to cover what those properties actually mean. As we start talking today, we're going to start with our acids, and one of the key features about acids is their taste. Acids have a tendency to taste sour, so I'm sure you guys have all tasted some sort of acidic fruit. For example, like an orange, lemon, lime, anything like that. Grapefruit is also a good example. All of those have citric acid in them, which is the same stuff that would be on the outside of like a Sour Patch Kid. Some of you guys, I'm sure, have had a green apple where it kind of makes your face pucker up. That's because it has more acid in it than a different type of apple might. But each of these things is just meaning that an acid tastes sour. Another common property of acids is the fact that they are caustic. You guys may have not heard that term before, but caustic means a substance that breaks down living tissue. Anytime that we have used acids in the lab so far, we've talked about the fact that they are dangerous. So what can they do to you? Well, if you don't have goggles on, of course that acid could get into your eye. And if you've ever seen an egg being cooked, that's similar to what an acid can do to an egg. Is if you get acid on an egg or acid in your eye, it actually changes those proteins and it makes it look like it's cooking. If you would get a very strong acid on your skin, it can eat through clothes, it can eat through your skin, it can eat through bone if it's really, really strong. That's why we always tell you to rinse that off as soon as you've noticed that you have something on you to help to alleviate any of those caustic properties. The third property that we're going to look at is the fact that acids are electrolytes. So remember, acids being electrolytes mean that they can conduct electricity. And the reason why this happens is let's look at something like hydrochloric acid, HCl. When it goes into water, what happens is it's actually going to ionize and make H plus and Cl minus. So because we have positive and negative ions in solution, it can conduct electricity. We actually saw this in the lights up, lights out activity with the different light bulbs, and the stronger that acid was or the more ions it had in solution, the brighter the light bulb was. When you're trying to identify acids, most of the time what you're going to see is acids are going to start with hydrogen or an H. So when you look at all these examples, we see hydrochloric acid, carbonic acid, nitrous acid, like all sorts of these, and almost all of them are starting with an H. There are a few that are not going to start with an H, like this one down here, acetic acid, but most of the time, if you see something that's starting with an H, you have an acid on your hands. Sometimes acids are going to be referred to as areneous acids. So what the heck does an areneous acid mean? Well, this means that an areneous acid is any acid or any compound that contains hydrogen, so remember, most of the time acids are going to start with hydrogen, and ionize into aqueous solutions to form hydronium ions. So right here is what we see is a hydronium ion, H3O plus, and it's +1, and that's its charge. Sometimes we get really simple with it, and we say H plus just because we're kind of lazy. So you guys are going to see me write it both ways as we're in this unit. So it could be H plus or H3O plus, both meaning hydronium. Another interesting property about acids is the fact that they ionize or they form ions when dissolved in water. So ionize means that they break down into ions or they are going to become charged. So acids are normally not charged, like here we see is hydrochloric acid. We have no charge on that. And then we're going to add it into water. Okay, so we do this a lot when we go and dilute acids for you guys to use in lab. So we're going to take a strong acid, we're going to add in water, and then what happens is we're going to get some ions out of this. Here I can see my hydronium ion, the H3O plus, and then in this case we get chloride ion from that hydrochloric acid, which is a 1 minus. Sometimes if we want to really simplify this, we write H plus Cl minus, and that essentially means the same thing because hydronium could be H3O plus or H plus, doesn't really matter. You might have heard some people talking about the strength of acids before. We were talking about the fact that sometimes in class we're using a strong acid or a weak acid, and the strength of an acid all depends on its degree of ionization. So we could either have strong acids or weak acids. Strong acids are going to be any acid that ionize or break down into their ions completely in an aqueous solution. So you get all ions from that one. None of it stays together as that bigger acid. Instead, when you get a weak acid, this is an acid that releases few hydronium ions in aqueous solutions. So if it's weak, that means that that substance really wants to stay together. So when we have our strong acid, like HCl, when it breaks down, we get H plus and Cl minus, okay? And we get lots and lots of these ions, okay? It's mainly going to be the ions. When something is weak, instead of breaking down into ions, most of it stay as that parent acid, and just a few ions are going to break down into it. That's what makes it weak, and if we were to test it with our conductivity tester, we would see that the light bulb would be dull compared to a very, very bright light with our strong acids. Here we have a list of a bunch of strong acids and a bunch of weak acids. I'm not super concerned that you guys remember all of these. That's not the biggest deal in the world. If you go to the back of your common ions to know sheet, our red reference sheet, you will be able to see that there is a list of acids that you should probably know. And of course, you're going to be able to use that on a quiz or a test. So you have that list available to you. Here we have our strong acids, so these are the ones that are going to completely ionize, and then we have our weak acids that aren't going to completely ionize, or they're mainly going to stay as this parent acid. So I'm not super concerned that you know which is which, just know that there are strong acids around that completely ionize, and then there's weak acids that are not going to completely ionize. One of the final properties of acids that we're going to talk about is the fact that acids have a pH of less than 7. Okay, so that means that we're going to be 6, 5, 4, 3, and so on and so forth. We can go negative, which is interesting. It's not just the pH scale of 0 to 14. You can actually go below or above it. So anything below 7 is going to be considered to be an acid. And the further away from 7 that you're getting, the stronger that that acid is also getting. So when you have a really low pH, like a 1 or a 2, that's a very strong acid. What that actually means is this means the concentration of hydronium ion, that H3O plus or H plus, is greater than 1 times 10 to the negative 7th m. And remember that m means molar, which stands for molarity or moles per liter. We have a few different reactions among acids that you guys are going to become familiar with. One of the most common ones that we're going to talk about and do some different experiments on in this unit is a neutralization reaction. A neutralization reaction occurs between an acid, like we've been talking about here, and then a base, which we're going to talk about next. So here we have a really common one where we have the acid hydrochloric acid. This is the same type of acid that you guys have in your stomachs. And then the base sodium hydroxide. Okay, acid plus a base. Anytime we add an acid and a base together, they go through what's called a neutralization reaction, and they're always going to create the same two things. And those two things are water and some sort of a salt. A salt is going to be an ionic compound like we see here, sodium chloride, a metal combined with a nonmetal, and then water. So that's probably one of the most common types of reactions we're going to see with acids are the neutralization reactions. Another reaction that we've actually seen plenty of times in class already would be the acid reactions with metals. We've seen hydrochloric acid being combined with magnesium in multiple occasions, including the World of Wonders, or World of Reaction lab, in that, what we're going to create is, in this case, we have magnesium chloride and then hydrogen gas. So anytime that we have an acid responding or reacting with a metal, we are going to see a release of hydrogen gas, or this is where things bubble. When we have acids, one thing that we want to do is we want to be able to tell, do we have an acid or a base as we're going through a reaction. So sometimes when we go through reactions like this, we're going to use something called an indicator. An indicator is a chemical that identifies acids and bases based on a change of color. So we are going to look at two different indicators when we talk about labs that we're going to do in class. And you've actually seen some of these in class. In the kitchen chem, you guys have seen litmus. And then in upcoming labs, we're going to be working more with phenolphthalein. Litmus paper. You guys saw this in kitchen chemistry, so we had different types of litmus paper. We had blue and red, and then we also dealt with pH paper. But litmus paper is always going to turn red in the presence of an acid. So if you have red litmus and you dip it in acid, it stays red. If you have blue litmus and you dip it in acid, it's going to turn red. The other one that we're going to be using in something called the titration is what we call phenolphthalein. Phenolphthalein is going to be colorless in an acid, so we're going to add a few drops of phenolphthalein into an Erlenmeyer flask later on, and right away it's going to look colorless, but that'll change once we add a base into it and start changing the pH. Last but not least are some properties of acids and the fact that we have different types of acids. So we are going to have inorganic and organic acids. When you think about this, this is probably the easiest way to go about classifying an acid as either strong or weak. When something is inorganic, it means it's made from something from the ground, but this also means that there's no carbon in it. Okay, so no carbon. When you see something that is inorganic, these are usually going to be strong. Okay, so just kind of keep that one in mind. Most of the time, those are going to be strong. Organic acids on the other side are going to actually contain carbon, and most of the time, these are going to be weak. So if you see an acid that does not have a carbon in it, most of the time you can consider it to be strong. And if you see an acid that contains carbon, like citric acid, notice how we have all these carbons in there, that one is going to be considered to be weak. That's why you guys can go out and eat a whole bunch of Sour Patch Kids and you don't end up with a bunch of chemical burns in your mouth because it's relatively weak. If you did the same thing with something like hydrochloric acid, you'd have a bunch of chemical burns in your mouth. Now that we've talked about acids, we should probably also talk about bases. So this is going to be the other side of the pH scale. And since we started off acids with taste, we should also do that with bases. Bases are going to taste bitter, so if you guys have ever just had black coffee, you're going to know that that's bitter. Dark chocolate is a little bit basic, or cocoa powder. You think that that would taste really good, and you put a little on your tongue, and you're like, ooh, that's really bitter. Another thing that you can think of is soap. So maybe you said some sort of naughty word in front of your parents when you were little, and maybe you got soap in your mouth, and that's a very bitter taste to it overall. You're going to notice some similarities between acids and bases, and one of those similarities is going to be the fact that bases are also caustic. So we already talked about the fact that caustic means it can break down living tissue. So an acid can burn you, but a base is an acid's evil twin. It can do exactly the same thing. It can absolutely burn your skin. It can absolutely burn your eyes. And that's why no matter if we're using an acid or a base, we're always wearing goggles in the lab. Bases are also going to be electrolytes, just like we saw with acids, so meaning that they can conduct electricity in solution, so they are also going to break down into ions. And then one interesting thing is the fact that bases are actually slippery to the touch. So if you were to get a base on your hand, like soap, shampoo, things like that, you're going to notice that it has that slippery type of feel to it, and that is very much a characteristic of bases. Acids really don't have a feel to them, but bases do. We talked about the fact that acids have the hydronium ion when they are going to break up, so we need to look at the Arrhenius base. And when we talk about the Arrhenius base, now bases are going to contain hydroxide ion, which is this, OH minus, and they're going to ionize into solution to form those hydroxide ions. So OH minus is going to be the hydroxide ion, and is going to be the ion that is characteristic of a base. We talked about acids on the pH scale of them being lower than 7. So bases are going to be opposite. Bases are going to have a pH above 7 or greater than 7. So 7 to 14 is generally going to be what we see with a base, but of course it can go higher than 14 as well, and if it's exactly 7, that's actually neutral, so that wouldn't be considered a base, but above that would be. So this means that the concentration of the hydroxide ion, OH-, is greater than 1 times 10 to the negative 7th molar when we have a base. Since we talked about indicators with our acids, we should also talk about indicators with bases. Remember, an indicator is anything that is going to change color based on what is happening to the pH, in this case, in the reaction. So we have 2 indicators again that we're going to use, same ones that we use with acid. We talked about litmus already with kitchen chemistry, and remember, litmus is going to turn blue when it's a base. So if we have blue litmus, we touch it to a base, it's going to stay blue. If we have red litmus, we touch it to a base, it's going to then turn blue. Phenolphthalein is the other one. Phenolphthalein is going to be pink in a base. So it's this very vibrant like highlighter pink that you guys are going to see when you have phenolphthalein inside of a base. Just like acids, bases are also going to have different strengths. So the strength, again, is going to deal with the degree of ionization. If something is strong, it's going to ionize completely or break down into ions completely in the aqueous solution. If it's weak, most of it's going to stay as that parent base, and you get very few hydroxide ions in that solution. The last thing I have for you guys on this one is the strong bases and weak bases. Essentially, what I want you guys to be able to do is if you see something that is ammonia, NH3, that's realistically the only one that I want you to know is a weak base. Everything else you can generally consider to be strong because most of the other ones that we're going to use are a lot more common, like the sodium hydroxide, potassium hydroxide, or calcium hydroxide. So consider most things to be strong. If you see ammonia, that's the one that I want you to know on site is weak. Okay, so those are the general properties of acids and bases. If you have any questions, let me know. Otherwise, have a fantastic day.